When we make measurements with isothermal calorimetry on biological samples that need oxygen, we need to make sure that we have enough oxygen in the vial and not too high concentration of carbon dioxide. Let me show you an example. We have samples of 100 barley grains, and the black curve shows nicely germinating grains with a high thermal power. This is 3 days measurement. They have plenty of oxygen because there is gas flow through or air flow through the vial. The green curve shows the same type of samples, but here the aeration was not successful. And we can see that they don't have enough oxygen, so their respiration slows down, actually goes down to quite close to 0. So there is a big difference between a sample with enough oxygen or a sample without enough oxygen. And calorimetrists working with biological samples needs to handle this. And the first thing that one should do is to think about this question: how much heat is produced or can be produced when all the oxygen in a vial is consumed? So let's make some simple calculations about this. And first of all, we have a vial, and it has a volume. That's an important parameter. Let's say in this example we have a 20 milliliter vial. Of course, that 20 milliliter, that's a gas phase, so it's the whole volume minus the sample volume. We have our biological sample there. Then we have the ideal gas law. PV equals nRT. And now we're interested in oxygen. The atmospheric pressure of oxygen is close to 21 kilopascal. The volume, that's the volume of our vial. The moles, that's what we want to calculate. R is a gas constant. And T is the temperature. Let's say we are doing an experiment at 20 degrees C, so then this is 293 K. So now we can calculate the amount of oxygen in a vial, in a newly closed vial, where the oxygen has not been consumed yet. And 20 milliliter, now this has to be entered as cubic meters in this calculation. Everything in base SI units. And if we calculate this, we get, I have made this calculation already, 0.17 millimoles of oxygen. So now we know how much oxygen there is in the vial. Now, how much heat will this produce when it is respired? Well, respiration is combustion. And for combustion, we have a constant enthalpy called Thornton's constant, or I call it Thornton's constant. So, nearly all organic compounds, when they are combusted in oxygen, will give this heat, approximately this heat, per mole oxygen that is consumed. And the T here, it is my nomenclature, but I like to acknowledge the originator of this, Thornton. And his publication, original publication, is 1917, The Relation of Oxygen to the Heat of Combustion of Organic Compounds. He essentially found out that all organic compounds, or nearly all organic compounds, when they are combusted or respired with the help of oxygen, they will produce similar amounts of heat per mole oxygen. And this is very useful for us. This other paper shows how one can use Thornton's constant in calculations in biological calorimetry. Now we have the number of moles, and we have this constant, Then we can calculate the heat. Q, that is 0.172, like that. And I'll skip the sign. This is an exothermal process. We will end up here with 78 joules. So if all the oxygen in a vial is consumed, we will get 78 joules in this case. Now, how can we use this? Let's take an example. We have made a calorimetric measurements, and this is thermal power. And let's say the result looks like this. And we are now here, and let's say it's after 20 hours, we have found that we have a mean thermal power of 300 microwatts. Now, thermal power, watts, that is joules per second, times the time in seconds, gives joule, gives heat. So this is the heat. The integral here is the heat. So the heat above here, that is the maximum heat that we can get when all the oxygen is consumed. So let's call that Q max. This is the heat that we actually have got after, in this case, 20 hours. And Q divided by Q max, in this case, sorry, I have to calculate Q first. Q, that is 20 times 3600, the hours times how many hours are per seconds are per hour, and 300 microwatts. That turns out to be 22 joules. That's the actual heat produced. So 22 divided by 78, that is 28. And this is the fraction of oxygen consumed, the fraction of the available oxygen consumed. And another way to phrase this is to say that we have 21% oxygen when we start. A 28% reduction is about 15%. So we have gone from 21 to 15% oxygen. A reduction in oxygen is up to 50% is maybe not a problem for many organisms. Depends on what organism it is. But if it gets lower and lower and lower, sooner or later we come to a critical level when the organism cannot remain at the activity it should have had if it would have been atmospheric oxygen concentration. So it's important to know how much oxygen that we have consumed, and also what the threshold is for the organism we are studying. Now there is another side to this, another gas, that we have carbon dioxide also. And the respiration process can be very simple, written like this. We have a carbon substrate, and we have oxygen that is consumed, and we have a carbon dioxide that is produced. We also have water here, and we have oxygen and hydrogen in the substrate here, but let's make it very simple. The question is how much oxygen is, or how much carbon dioxide is produced for every oxygen that is consumed. This value is called the respiratory quotient, and well, the moles of carbon dioxide divided by the moles of oxygen. And this has a value of 1 for carbohydrates. When the substrate is carbohydrate, and a value of 0.7 for lipids. And that's the range we have. So in many cases it's 1, because carbohydrate is a very common substrate. In extreme cases where it's only lipid, we have 0.7. A note here, an important note. This is at steady state. when we have the same respiration for a long time. If things are changing rapidly, a respiratory quotient measured during a short time could have very different values. So let's make it simple. Let's say we have this case. So for every oxygen molecule that is consumed, we have a carbon dioxide produced. Then we have time, and we start with 21% oxygen, and it's being consumed, let's say like this. And carbon dioxide starts at, well, essentially 0, very low values, and it will increase. So if we, in the previous case, we had a reduction of 6%. Let's say that this is somewhere here, at this time here. We had a reduction of oxygen with 6%. At the same time, we will have an increase in carbon dioxide. So if this is minus 6%, we will have plus 6% here. And in many cases, this is more important than this, because many organisms are sensitive to high levels of carbon dioxide. There are, for example, insects that die if the carbon dioxide level is increased too much. So it depends on the system. These calculations of how much oxygen that can be consumed and how much oxygen that is consumed, and the calculations with the carbon dioxide, these are very useful, but to use them you have to know something of your own system.